So now picking up the point with the tail functions, with the tails of the function, of probability functions, from the empty space problem it follows that the tails of the distributions, as I said before, become extremely important. So here is the mathematical foundation for that. We consider a standard density function like this one here, traditional Gaussian distribution, where the maximum density, probability density, is around the mean. And we consider a slightly different function, f prime here, which is 0 if the probability function, probability density of f is smaller than 1%, and else is it's the probability function density of f of x. Yeah? And rescaling f prime to a density function will make very little sense, or very little difference in 1D, because very few data points just fall into this first case. So very little or very few data points end up in being 0 for f prime, because all of for most of the values of x, f of x gives a probability more than 1%, which is something down here. So only for those observations to the left of this mark here and to the right of this mark here, f prime would give 0. And obviously, giving this probability density function, it's extremely unlikely that this occurs, that those x are actually observed. Yeah? So in 1D, that's no big deal. However, for high-dimensional data, this is completely different. Yeah? So it may be that more than half of the data set has less than 1% of the maximum density. So if we consider that the mean of f or of x, the Gaussian distribution x, the observations, the set of observations x is 0, then, for example, in a 10-dimensional Gaussian distribution, we see that this relationship between f of x and f0 is something like this one here. The median of the g-squared distribution, which is down here, with 10 degrees of freedom, 10 is the number of dimensions here, is something 9 point something. So the median of this one here, it comes down to e to the power of this one here, yeah, which is the Gaussian, the g-squared median here, which is less than 1%. Yeah? So most of the objects now occur at the tails of the distribution. So most of the points now in 10-dimensional space would fall into this first function here, yeah? Into this first case here. Or in other words, in contrast to the low-dimensional case where we assume, or we not only assume, we can expect that most of the points are around the mean. Now most of the points are in those tails here, down here. And this is something completely unintuitive, but extremely important, because these very low density regions are now covering most of the data points. Yeah? So here is an empirical example how that scales with dimensionality. So this one gives you a radius of the sphere around the mean, yeah, the mean of the distribution, and this is the probability, probability density. And you see here for a radius of 1.6, so you go in around the mean in this left direction 1.6, in the right dimension in the right direction 1.6, and in the one-dimensional case you are still 90% of the data points are covered by this radius. Yeah, so 90% of the data points are within 1.6 around the mean. We have mean equals to 0 and a standard deviation of 1. But of course, with different standard deviations, a different picture, but the relationship remains the same. So now if you go up with the dimensionality, so here is the two-dimensional case, so the curve looks like this one. So here for the same radius now, it's not 90% anymore, it's roughly 70% anymore. Yeah? And if you go down here to 10 dimensions, this is the curve for 10 dimensions, it's 99% of the mass of the distribution is not within the sphere. Yeah, this is the mass, this is the number of points that are within the sphere. It's all of the points are outside of the sphere. Yeah? So they are in these areas here around the tails of the distribution. And again, this is very important because it's extremely difficult to estimate density, expect for enormous samples. Because we need in high dimensional spaces virtually the entire sample at the tails, and so it's hard to estimate the correct distribution actually. Yeah? So tails now get important or become important, and that's extremely unintuitive. Yeah, there are some further problems. We are not going into detail here, but just to mention them, well, patterns and models in high-dimensional data are of course sometimes or very often hard to interpret. Yeah, for example, we have a long decision rule, like a decision tree grows, of course, and decision tree is a good and very well interpretable model, but if it is very high, then it tends to be not so easy to comprehend, of course. Yeah, so I think that is a very clear and even trivial thing. Efficiency in high-dimensional space is also very often limited. You may know from, for example, from the database 1 lecture, there are some index structures to support similarity neighborhood queries, and those index structures typically degenerate very quickly when the dimension grows. Yeah? For very similar regions, and also distance computations are of course more expensive, but the most important point is that the index structures, that typically they are search trees, and these search trees completely degenerate when the dimensionality grows. And we are not talking about 100 dimensions, but these index structures typically degenerate with 6, 7, 10 dimensions, and then sequential scan is a better idea to search for neighborhoods. Third thing is there may be, and this is coming back to the baby shape game, there may be of course different semantic layers. So we didn't capture that so far in those mathematical stuff here, but there may be different semantic concepts and also different semantic patterns, and those may be only observable in subspaces or projections of the original features. Yeah? Think about this example that we have 10 features, 5 for shape, 5 for column, for color, and if we pick the 5 for shape, we get the pattern for shape. If we pick the subspace of the spanned by the 5 for color, we get the color patterns. Yeah. So and it may be that you are only interested in one, but it may be also that you are interested in all possible semantic layers, semantic concepts, semantic patterns that are in there. That makes it even harder. Yeah, and the last point is that, of course, correlated features are somehow redundant features, and if you have a lot of redundancy, this redundancy may dominate other things. So cliques of correlated features may dominate object descriptions, patterns, whatever. Yeah, so object descriptions or data patterns, yeah, in a sense. So this may also be a problem. The whole thing is we talked about the curse of dimensionality, and that high dimensionality is really a strong limitation to many data mining algorithms, and actually this is only one side of the coin. So every year in the summer we have the case Kröger against TRESP, because TRESP has the machine learning lecture, which is also held in summer, and typically he tells you a little bit a different story. So we have the 2 points here. So Kröger says dimensionality is a curse. I just told you why. And Treff says, well, not in general. The kernel trick, you may remember, shows the opposite through the extension of the data space with new attributes. Yeah, so we had the trick was that we wanted to apply, for example, a linear model, support vector machine, but the data is not linearly separable. You cannot separate them with a linear model. But for example, with a quadratic model, so the kernel trick derives new attributes, so pumps up the feature space such that the mining algorithm, for example, this support vector machine, can now do its job. Yeah. So in that case, and that is the point of Treff, is dimensionality is a blessing. So who is right? Is it a curse or is it a blessing? Yeah, and the answer, which is probably not really satisfying, but maybe a good one, is we are both actually right. And you might say, "What the fuck? What are you telling me here?" But you have to have a closer look at this point, and I think this is a very, 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 very important point. So that's why I'm emphasizing this here even more. So what is the point? Well, in our case of the curse, look at what we have assumed. Yeah? Attributes, we have assumed attributes, features are independent and typically also uniformly distributed. Yeah? So these attributes are very likely to be completely irrelevant for the data mining task. If it's just a uniform distribution, what kind of pattern you would expect? Nothing. That's exactly the point. Yeah. So as long as you have uniformly distributed features, they are just noisy features, you end up in a curse. And of course, the more attributes you have, the more features you have, the more likely it is that you get irrelevant features. On the other hand, the blessing says, well, if you add relevant attributes, really, really relevant attributes for your task, and pumping it up with derived features that somehow express this quadratic relationships or quadratic patterns, for example, in a quadratic kernel, that works. You add relevant attributes. Yeah. So even if you add more relevant attributes, so pump up the curse, it is a blessing. Yeah. So the message is high dimensional data is quite tricky, and the curse can come by several problems, but typically it's due to irrelevant attributes. So try to get rid of irrelevant attributes that have nothing to do with your data mining tasks. The question is how to identify them. We will cover that next week, and try to keep the relevant ones, of course. Some of the problems are instead of relevant attributes. So among the relevant attributes, try to get rid of the redundant ones. So if you have redundant attributes, they of course dominate or tend to dominate the rest. Yeah. So you want to get rid of those two types of attributes: the irrelevant ones and the redundant ones. And we will take care about these two things in the next subsection, supervised feature selection, and also later on in feature reduction and clustering high dimensional data. And that is coming up next week. So I hope you are in the mood for more here. Stay healthy, stay tuned. See you there.